I guess I'll start. I'm Lauren Milechin. I'm from MIT Lincoln Laboratory. And today I'm going to talk a little bit about how to build scalable tools for open edX learning analytics. So just to kind of give you a roadmap of what I'm going to talk about, first I'm going to kind of introduce what we're trying to do at Lincoln Laboratory, give a little bit of background about the tools that I'm going to be using. I'm going to show a short demo with those tools, and then I'm going to go over how we kind of validated our approach using some ground truth data and what the results were, what we could capture using the tracking logs. And then finally, talk a little bit about kind of our conclusions, what sorts of things we want to do in the future, and what we might need from the open edX community. So at Lincoln Laboratory, we have our own installation of open edX that we call LLX. And our goal is to provide online, self-paced, and blended professional education to our community. So that might be other employees at the laboratory. That could also be sponsors that we have for various other projects. And us on the LLX team, our main goals, there's three of them. First is to provide education to assist the DoD in fulfilling its education needs. The second is to transition other Lincoln Laboratory technologies, whether that be to other employees within the organization or to sponsors as well. And to also explore the pedagogy of new learning and teaching paradigms, because the better you can teach something, the better that technology transition can happen. So in order to do that, we're really interested in adaptive learning. So that's it comes in three different categories. The first is content-based adaptive learning. So we're really looking at what background does the student have and what do they need to know in order to understand the material in the class. So maybe that means they can skip certain sections or they need more information in a specific area. The second has to do with how you deliver the material to the student, and that's completely trying to figure out what the student's learning style is and how does the student learn best from that material. The third is the pace. So some students kind of go through material very quickly and they just kind of want to get it done and figure out exactly what they need, and other students like to take their time and really pace themselves through the material. So if you can adapt to these three things, you can really yield deeper learning for their students. But in order to do that and build these models to get a better idea of how you can do adaptive learning, you need to understand how the students use the resources. And in order to do that, you need the data. So open edX currently offers Insights, which is a great tool for instructors to see how the students are interacting with the course. However, kind of on a more research level, you need a lot more information than kind of Insights can provide. So we started looking at the tracking logs. Fortunately, at the lab, we do a lot with data analytics and building up these pipelines for analyzing different types of data, and we have our own tools to do this. So one of those is Deform, which I'll talk about in depth later. So we do our own data collection from the tracking logs. We parse that data, we get it into a form we can analyze, and then we will eventually start doing a lot of that pedagogical research that we want to do. And we do that using data from our courseware. So some analytics that we're really interested in involve kind of three main areas. First is to see kind of what completion statistics are. So how much of an entire course people are completing, which individual sections and units are people most interested in, and which videos are being watched to completion or maybe part of that. We also want to see which units and sections get the most attention, which videos receive the most attention, which problems are more troublesome, and that'll kind of help figure out which sections might need to be reworked. Or maybe kind of from the adaptive learning point of view, maybe those are the sections that we need to kind of point people back to more often. And then finally, we want to know what kind of the typical student paths are through the material, whether the student is maybe a linear learner and just likes to kind of go by the syllabus one after the other, or whether the learner likes to jump from topic to topic. So these are kind of some example simple analytics that we've made so far. The first are total different types of video events, so the number of plays from start, the number of plays from within the middle of a video, the number of seeks. You can see students like to seek around in the video a lot to kind of find what they're interested in. And then the second is the percentage of correct answers within different modules. And you can see as the material gets more complicated, the number of incorrect answers increases, which makes sense. So now I'm going to talk about the tools that we use to get at these analytics. So first, I'm going to talk about Deform. It stands for Dynamic Dimensional Distributed Data Model. And if you ask me later what it stands for, I probably can't tell you because I always forget. It's a lot of Ds. So this is actually just a library that will allow you to represent your data in a very specific format called an associative array. It allows you to manipulate your data using linear algebraic operations. And it also allows you to connect to and query high-performance databases. So it kind of allows you to do a lot of the things that you would want to be able to do with your data. Now, associative arrays, or at least two-dimensional associative arrays, which we use here, are two keys mapped to one value. It's kind of a mathematical or a data structure, if you think of it that way. And you can think of it theoretically or logically as a big matrix with string, row, and column indices, as opposed to usually with a matrix you think Aij, where I and j are integers. Here they can be strings. And these are sorted lexicographically, so you can really easily find parts of the associative array that you're interested in. Because of this matrix kind of form, you can easily represent graphs in this form, which is really great for trying to figure out what a student's path is through the materials. You could think of the material of the course as a path with connections between the different sections, and the student's path would be a path through that graph. There's kind of two other nice things about associative arrays. They're closed under algebraic and set operations. So every time you do an operation on an associative array, you get another associative array back, which allows you to continue to do more operations on it. And finally, it has composable array indexing, which allows you to index into an associative array and get another one back, and then you can keep doing the operations you want to do. You can download it. It's open source at deform.mit.edu, and I'll have this link on the last slide as well. Yes? Oh, okay. 10 minutes and then 5 minutes? Yeah, both. Thank you. Okay, so why use Deform? Why not use one of the many other tools out there? So the first is kind of the flexibility of associative arrays themselves. They can represent a diverse different types of data. So you can represent graph data. You can represent something that would be maybe documents and items, and triple store is very flexible and all that. And they can also support a large variety of linear algebraic operations and other operations as well. So not only can you represent a wide amount of data, you can actually do operations on that data. You don't just put it in there and then it sits there. You can put it there and then you can actually do things with it. Deform itself is really easy to set up and use. You essentially just download the library, add the directory to your path in either MATLAB or Octave, which is currently what Deform supports, and then you can just start working. And with Deform, a lot of native matrix functions and operations that work in MATLAB are overloaded, so you can use them with associative arrays. So you can use matrix multiplication, for example, the same way you would do with two matrices. This makes it really great for rapid prototyping analytics that you're trying to figure out how to do on a larger scale, and also do interactive data exploration to try to figure out exactly what you're looking for in your data. Finally, if you have the right schema, if you organize your data the right way, it's really easy to query for and really drill down to the exact data that you're interested in. So in addition to Deform, we have developed this thing that we call the analytics pipeline, and it's essentially a formalization of all the steps that you do to get your data from its raw state when you first receive it to something that you can analyze, visualize, and extract actionable information from. So in short, these steps are first to get your raw data, to parse it, to ingest it into a database if you need it, to query the database or scan your files that have the parse data in them, and then finally to analyze and visualize your data. So the first step, retrieving raw data, specifically when we're talking about Open edX data, that all appears in the Open edX tracking logs. These are located in the course platform VM in JSON format, and we essentially just set a job that transfers that data daily to the system that we're going to be doing the parsing and all the analysis on. And this is an example kind of a nicely indented line of that JSON. So this is a course enrollment action when I initially enrolled in the Advanced Database Technologies course, which I'm going to be using as an example throughout this talk. So kind of where the meat of this pipeline is parsing your raw data. So in this example, we're parsing from JSON to Deform format. The parser is written in MATLAB, and we currently save out the parse data in mat files, which, if you're not familiar with MATLAB, allows you to save MATLAB variables in a file. The row keys, if you remember, if you think of kind of the sparse matrix representation where you have row and column labels, the row labels are referred to as row keys. The column labels are referred to as column keys. The row keys here are unique identifiers for each event. So each row represents one line of the tracking log. And the column keys represent attributes and their corresponding values, so we can concatenate them together. So we start here. This is kind of a little bit of the JSON username, Lauren, and then we just kind of push it together and put a pipe in the middle to tell what's what. Okay. And then the value, since it is a triple, is just 1. So to show you what this looks like, here's the, sorry. We have first the raw JSON file, and we parse it into the Deform associative array, and this is kind of like a triple representation. So you can see that the row key is all the same in this one because I'm only showing one row of data, and it's going to give a triple for each entry in that row. And these, in the second thing there is the column key, which gives you kind of the attributes and the values in that row. So you can kind of look at it and see what's going on. There's something happened in this course, ADT, and it was an enrollment action. The username was Lauren, things like that. And here is sort of a way you can like logically picture it, is this big matrix with ones and zeros or empty spaces, however you want to imagine it. Rows are individual events, and columns are kind of individual pieces of information. Okay. And at the parsing step, you have a unique opportunity where you can kind of add in extra information that you feel like would be helpful, or remove information that you know you're never going to use. So here, we notice in the tracking logs, they contain a lot of like section IDs, but those aren't very human readable, so we added in the section and unit names and module names as well. And then also whether an event is a page navigation or explicit. I don't know how many people have looked at the tracking logs, but there's a lot of events that are kind of just issued by the server and not very interpretable. And then there's events that are obviously page navigations, people moving from one page to another. And then there's events that are specifically issued by the platform. And the page navigation events and those explicit ones are the ones we're most interested in. So we remove kind of these extra server-issued events. Step 2, we call ingest. So if you're going to be using a database, this is when you would ingest it, once you have your parse data. Deform associative arrays can be easily ingested into a variety of different types of databases. Right now, kind of where the strength of a database is when you're often going to be looking for a small amount of data in a very large amount of data. Right now, the amount of course information we have isn't that big, so the file system is perfectly sufficient to store that data. When we move to a database, we'll probably use Accumula, which is a nice NoSQL triple store database that's great for large sparse data, which this will become. And the added benefit of that is Accumula supports what's called cell-level visibility labels, which allows you on the individual piece of data to label it who's allowed to see that piece of information. So for example, you can ensure that instructors will only see their students' data when they're querying the database. So because Deform easily connects with all these different databases, all we need to do when we want to ingest it is just to load the data into memory and ingest it. It's one command. Okay. So when you finally get around to wanting to run your analytics, first you have to get the data that is relevant to your analytics. So for example, if you're an instructor in one course, say, you only are interested in the events that occurred within that one course. Deform, this works by retrieving relevant rows by specifying columns of interest. If you remember, the column key contains kind of a lot of that data that you would be searching on. Oh, sorry. This is what I just said. Okay. So here I have an example of a query you might run, actually the one that I just said, where you're specifying sort of the course ID by saying, okay, this is an indexing into A, which is an associative array. Give me all of the columns where the course ID is ADT. Give me the row IDs stored in here, and then look in A, get me all those rows for those row IDs and store it in there. And that takes you kind of from this logical representation where you have a couple different courses down to here where you have just this Advanced Database Technologies course and then all of the information associated with those events. Okay. Finally, you're ready to analyze and visualize your data. And this step completely depends on what your goals are and what you want to do and what sorts of insights you want. As I said, Deform associative arrays support a multitude of operations, including addition, subtraction, matrix and element-wise multiplication, summing, etc., set operations, all those. And if you're interested in graphs, one matrix multiplication on the columns that you're interested in will give you an adjacency matrix representation of that graph. And this is nice because most graph algorithms can be expressed in terms of matrix operations on the adjacency matrix. So you're kind of all set to just start plugging along. Okay, so these are kind of two short examples of little simple analytics that you could do. The first thing that I do is form an adjacency matrix of unit transitions. So when a student moves from one unit to the next. And then I look and I see there's 150 unit transitions. And then this, if you use greater than, less than an associative array, it does comparisons on the value. So this says what are the unit transitions that happen more than 7 times. So for example, people moving from the goals to the course overview, that kind of makes sense. And then here we have kind of a visualization of that adjacency matrix. The second one is a very simple thing. We're just looking for what are the questions that people provided the most incorrect answers for. So first we filter on incorrect answers, and then we look and we say, what are these questions? So for example, we had this question, the last one here, which of these is an example of big data, select all that apply. And this question actually ended up being troublesome for people, so we needed to rework it. So these sorts of things can be very useful to really see kind of where people are having trouble, what you might need to rework or add more information for. Okay, so I'm going to do a very quick demo to show this process of building the graph and then answering a couple questions. So there's kind of a lot of stuff here. The most important thing is you just load the associative array, the mat file, it's called course data, and you get this variable in MATLAB called A, and it has 1,600 rows and about 3,200 columns. So that means there's 1,600 individual events and kind of 3,200 attributes associated with those. Now, first thing we're going to do is create that unit change graph that I talked about before. And you can see there's 27 by 27 units. So there's 27 total units in the course, I guess. And so it's a symmetric matrix. That makes sense for the most part. And then this is what it looks like. It's a slightly different, It's a slightly different data set than the one I was showing earlier, which is why it looks different. And the one that I've selected was the unit transition from the associative arrays unit to the Deform basics unit. So it's related to what we're talking about now. Okay, so now what we're doing is creating another graph that has one vertex type, the unit, and then the other one, the event type. So we're looking at what events are occurring on which units. And then further, since we've already captured the unit change events, we're removing those using subtraction, essentially. So those are events that start with SEQ. And then we're also removing all the navigation events as well, because we're not interested in those. So you can see just by subtraction, you can kind of get rid of the things that you don't want, which is very nice. And we end up with an adjacency matrix that looks like this, and point out a few things. So like this one here is load video, this is pause, this is play. So all the video events kind of like have the same pattern, because those are the units that have videos on them. Okay. So next, we're adding those two graphs together. So by addition, you can combine two graphs, which is pretty cool. And this is what it looks like. You kind of have the second graph is smushed here, the first one's smushed there, and the reason is we still have all these prefixes and they're different. So just to show you that it's quick and easy to do, I'm not going to go through it. You can quickly remove all these prefixes, and then you just get the unit name, and then you have the prefix down here. You could remove those prefixes if you wanted to also. And then you kind of get the graph more together. So 3 questions that we can answer with this with 1 line of code, which is nice. So first is, which units have the most video plays? So you just kind of select down to the play video attribute, and then you say, give me all the values greater than 10. So let's see, which one is it? The MATLAB co-occurrence and threshold has the most, and actually the events that are there, the videos, are ones that people have to refer back to a lot or have more complicated information in them, which makes sense. Second, what actions do students take from the associative arrays unit? So where do students go from a particular unit? You can look. Or what actions do they take? So there's a lot of video events because there's a video on there. You can see they move to the Deform basics unit, which is the next unit. And then which units have the most activity? You can do a sum across the columns of that graph and then just say greater than 40. And you can see Deform basics has 158 events that occur on that video. And the reason that happened is we had someone who was watching the video and kept seeking because people kept interrupting her while she was watching the video, and she kept having to go back. Okay. So in order to verify what we did and kind of make sure that what we were seeing in the analytics was what was represented by what people are doing, we went through and created some ground truth data. So the questions we wanted to answer was, can we accurately recreate a student's actions? Which actions are captured by the tracking logs? Which lines of the tracking logs contain the most useful information? What does the parser need to add or remove in order to get clear, informative events? So what we did is we created a script of actions for 3 students and 1 instructor. And one of my colleagues went through, executed each of these events, recorded the time and any comments that she had while she was doing it, anything she noticed. And we did this on our Advanced Database Technologies course. So these are kind of an example of what she recorded as she was going through. So this is one student, student X, logged in, did a drag and drop problem, kind of got it wrong, got it right, things like that. And then instructor events as well, because we're interested, what can we capture from the instructors? And again, kind of went in, looked at a problem, went into studio, did some other things. So that's what our ground truth data looks like. And then, this kind of looks familiar from the other slide. This is kind of what, when you're looking at the raw Deform line by line, this is what you would see. So this command here says, give me the first line of Deform of this associative array for student X. And you can see that the student logged in based on kind of the refer field. You can see what time that the student logged in, that the student was taken to the dashboard, and that this is a navigation event. Okay. This is a more interesting line. This is an answer, a question that a student answered. So you can see things like the current unit, whether the student got the answer wrong or right, what was the question that the student answered, the fact that this is a problem check event, and what answer that the student provided. And then there's things like attempts, how many attempts has the student made. Okay. So we'll get into results. And so on this side here on the left, we have the original ground truth data. And then on the right, we have similar format, me going through the lines of D4M and trying to recreate what the student had done. So there's a lot going on in the slide. I'll kind of point it out. Does this work? Oh, and it didn't obviously render nicely, but it doesn't work. So up at the top, one thing to note is that the platform reports time in UTC. So that was kind of different from what I saw and what was recorded. Drag and drop problems, it was kind of hard to capture a lot of the things that the student was doing. The only thing that we got was what the student input. And then even what the student input was kind of difficult to read because it specifies positions as opposed to like things. So as a researcher, that's hard to tell exactly what's going on, why the student got it wrong. And sorry. So for some reason, a single navigation got split into 2 in the logs. The platform, when there's a seek, when there's a caption seek, it says what the time is that the students seek to, but not like the line in the caption that they clicked on or the word that they clicked on. And the platform reports time in seconds as opposed to maybe minutes and seconds, but that's not a big, it's just a thing that I noticed. Okay, so kind of a summary of all of the things that I noticed going through here. We can capture the general path of the student, which is really great. We can kind of get general events that the student is doing, that they're answering questions or they're playing a video. We can get page and navigation events, module, section, and unit changes. But there are other events that are either not reported or not easily interpreted, such as when a student clicks on a file to download that's not reported at all, clicking on a send email link, actions associated with the drag and drop problem, so actually the physical dragging of an item to the location. The answers to the drag and drop problems are kind of difficult to interpret, but that might depend on how you set up the drag and drop problem in the first place. I'm not sure, because it's already kind of difficult to put together. Overall, you can capture most events, and they're tracked by the platform, which is great. Okay. So I'm getting to conclusions. So we built up kind of these scalable tools for prototyping analytics using the tracking log data from edX. This work is kind of really for the researchers that are trying to do kind of more like the pedagogical research and adaptive learning, but also instructors that want to really customize their own analytics and kind of really dig deep into the data. We were able to recreate student and instructor actions from known ground truth data. And in the future, we're interested in building up more learning analytics. So if any of you have any analytics that you're really interested in, that you want to see done, feel free to reach out to us at Lincoln Laboratory. I can give you my card. And we'll see, that'll help us kind of drive like exactly what we're aiming towards. And we're specifically interested in a student's path through the material, because that can really start getting at how do we adapt these courses to what the student needs. We eventually want to build models for adaptive learning to enable them, and to be able to assess and recommend additional actions that should be captured through the tracking logs as well. Finally, one thing that I'm kind of excited about doing is ingesting the data into Accumulo and use Accumulo's visibility labels to really see how we can enforce privacy for the students. And finally, there's a lot of people who help out with the LLX instance, from content creators to people heading the program and people who actually like install edX for us and get it running. So that's big help. And then again, the link for Deform if anybody wants to grab it and try it out. It works in MATLAB and also Octave, which is an open source version of MATLAB that anybody can download and use. Okay, does anybody have any questions? Yeah. Or
So I have two related questions. One is what's the data size you're dealing with, like in gigabyte, for example? And second is how long it's going to take to process,
yeah.
by the scan phase.
So we're very early in sort of a lot of the developing courseware, and we've kind of just started getting beta users to use the course and transitioning them to other places. So our data size isn't that big yet, but I've used this technology on bigger things. For example, like Twitter data coming in, and usually for a day's worth of Twitter data, so that's about 10% of tweets, it'll take under an hour to parse all of that and ingest it. So does that give you a good idea? Yes.
So I had a similar question as well, but another question that came to my mind right now is are there other, so this is based on MATLAB and Octave, but are there other libraries that can do associative arrays like these?
So I believe it's implemented in Julia currently, which is an MIT thing. I don't know if there are plans. VJ knows a little bit more to do anything else. It's kind of
working on Python if there's enough. They're very similar to some of the dictionaries and key mappings that are there.
Yeah, it's based on demand,
But really,
essentially.
the big thing is linear algebra.
Yeah. So the big thing is the language, whatever we put it in, needs to have the linear algebra support, since it's so linear algebra driven. Okay. Have any more questions? Yes.
So does the pipeline work on incremental data, or does it start from the beginning of the tracking logs each time?
So you can set it to do however you want. So the nice thing about the pipeline is it's sort of a generalization of all the steps that you do. So you could take things out. So you still use the pipeline, but not use Deform. Use your own thing that you're interested in. Set a job to only look at the files that have been put there in the past day, which is probably what we're going to do.
Second question.
Yes.
So the data that you end up with in your database, is that looks to be aggregated, or can you get it for each user?
So we would just do a query to get that to get
each user.
for each user. Yeah. So it's lexicographically sorted by row key when you put it in Accumulo. So it would be kind of almost time-based because the row key is approximately associated with the time. But what databases are really good at doing is grabbing that. So, any more questions?
I have a suggestion.
Yes.
I think it might be useful, to attach the concept of context to events. These data things like people ask, how many times did a particular student post to the forum, for instance,
Mm-hmm.
and, do students who post to the forum more complete the course at higher rates? But if we think of questions like, okay, how do the forums actually help MOOC learners so we can leverage its value so like, things like student X visited the forum while she was viewing this video or
Yeah.
after answering this question incorrectly. This takes a lot of cleaning and
It's-
processing the data. So if you guys can solve this problem for the rest of the data, that would be something amazing.
Yeah, and basically, like you said, it's a difficult problem to kind of see. You're looking at an individual line in the tracking log. How do you say, okay, what happened right before this? And part of that is to be able to get that graph representation to really see what was the path. Yeah. Any more questions? Yes.
Could you compare using a tool like Deform with something like just like a standard relational database? So you, for example, talk about building a path, like with window functions, for example, you could very easily just look at the previous row or like the previous 10 minutes or something like that.
So the nice thing about the graph is it's very transversable, whereas if you're just kind of looking at the last row, you can start in one place and look at the last row, but you can't then maybe look at, and then of course it depends how that data is organized. Relational databases are very sensitive to what the schema is and how that is, so it might not be as easy to see, okay, the last row, what if that's not even the same student, say, for example, the way your schema is organized. So when you have sort of the semi-structured data, a lot of times relational databases don't exactly mesh well with that. When you have a lot of, so for example, if you wanted to look for all of the questions that had a particular word in them or something like that, it's very difficult to ask a relational database that sort of question, have it answer in a timely fashion.
Maybe also a question for clarification. Is Deform, is it containing entirely event-driven data as opposed to like relational data for grades and other stuff that you might get from the site?
So you could get at that data sort of by looking at what you would have it, kind of the idea with like the NoSQL approach is you have one big table, or at least the Accumulo approach, and you have one big table and you have all that data in that big table. And maybe you want to know what question that a student got wrong, which students got those questions wrong. And then you kind of get the student IDs, and then you can look, okay, what events happened by those students, and then you can kind of get back, oh, what other questions did that student get wrong? So everything's kind of in one central location, and you can pretty easily kind of go in and get a lot of data that way. Does that make sense? One more question. Yes.
Is it any manual to deploy and install all this stuff?
No.
No.
So you can download the Deform tool, which would allow you to
Yeah, but
write your own parser.
I've already opened and downloaded, but it's not clear how to use it. Okay.
Okay. Yeah. Thank you, everyone.